Hello, everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenters today are Scott Gibbs from Thermal Analytics and Pierre Nubel from Oktal-SE. Scott is a senior engineer and leads the EOIR engineering team here at Thermal Analytics. He has over 18 years of experience in the defense industry with an emphasis on thermal and EOIR signature prediction. Other technical efforts for Mr. Gibbs involve field test validations of military vehicles, synthetic scene creation, software training, facilitation, and support, software development support, and contributions to the first female physiology for TAI's human thermal extension. Pierre has been working as a senior sales engineer at Oktal-SE for the past 7 years. He has engaged with diverse users of Oktal-SE software both within France and internationally, addressing a wide array of use cases primarily within the EOIR domain. These include conducting target signature studies in complex environments and contributing to strategic R&D projects for the design of future critical applications. More recently, development of a specialized offering aimed at meeting the growing demand for massive sensor data generation tailored for AI applications. So throughout today's presentation, you may submit questions in the question box, which we will review at the end. We are also recording this webinar and we'll be sending you the link to the recording following this presentation. And with that, Scott, if you're ready, you may begin.
Great, thanks, Chris. Good morning, everyone, and thanks for taking the time out of your day to join us here. I'm Scott Gibbs, and with me here is Pierre Nubel from Oktal-SE. And in this webinar, we'll be discussing how to incorporate high-fidelity MuSES target models into SE Workbench EO scenes. And I'll be passing parts of the presentation off to Pierre as we explore combining our software applications for advanced scene simulation. Next slide here. Okay, so for the agenda today, I will cover a brief introduction to MuSES and what that simulation code can do. We'll talk a little bit about the target model library that exists for MuSES. Then Pierre will give an introduction to Oktal and talk about the coupling process. He'll then show some rendering examples, a few demonstrations, and some other scenario examples to show what is possible with the coupling. And then I'll wrap things up with some thoughts on future and advanced applications. So we'll kick things off here with an introduction to MuSES. So our flagship software, MuSES, is a thermal solver and infrared rendering program. Inputs to the software include a 3D CAD geometry description, part material thicknesses, and thermal properties, and component heat sources as well. Boundary condition setup includes definition of environmental sources like the sun, sky, and background for radiation exchange, and air and temperature and wind speed for convective heat transfer. Outputs from the model include physical temperatures and 2D sensor renderings, which can be generated for any waveband from visible to long wave IR. And the rendering calculations can be performed broadband or spectrally and can take into account specular and diffuse reflections. The rendering output can also provide contrast metrics such as DTRSS and contrast radiance to quantify how different the target signature is from the background or gauge how acutely the target sticks out from the background, I guess you'd say. MuSES is a complete thermal analysis tool, and that means that all modes of heat transfer are accurately computed to give a comprehensive thermal solution. Radiation between surfaces, radiation from the sun, and from the exchange with the background and the sky, view factor exchange between geometry and all the clutter in the scene, all of this is automatically handled. Convection can be accounted for in a number of ways, depending on the model complexity, and conduction is also included both vertically and laterally through the mesh. Dual band radiation is employed during the thermal solve, so we deal with radiation in two averaged bands, one for the longer wavelengths involved in the face-to-face radiation heat transfer, and the other one for high intensity short wavelength sources such as the sun. And we can also incorporate environmental effects on our simulated model. So with our transient solution, the position of the sun is going to be calculated for every time step. The view factor between the sun and the geometry will get recomputed. And the strength of the sun is going to change throughout the day, affected by cloud cover. So you're going to get direct and diffuse solar reflections off of geometry and terrain. And we exchange long wave radiation with the sky as well. And finally, MuSES has built-in capabilities to model heat sources like the engine, exhaust, cooling system, and electronics. And it can also vary the operating state or environmental conditions over time, which is very handy. So here's a high-level look at the simulation process with MuSES, where we've got some target of interest and we acquire a 3D geometry. We prepare a surface mesh and bring that into the software. We then use the material database to specify the materials that different parts are made out of, the thicknesses of those parts, and any heat sources in the model. And once that's done, the GPS location can then be set to capture the time of day, the season, day or night, and the weather data for the time of interest, as well as the mission profile, which we'll talk a little bit more about. But you know, whether the engine is on or the vehicle is stationary or moving. And if you desire to move beyond physical temperature prediction, then you can input sensor parameters like the resolution of your sensor, the waveband, the field of view, the atmospheric profiles, and ModTran is used to aid in generating a sensor radiance rendering like you see on the right-hand side there. So as I said, the inputs to MuSES are shown on the left here, and I've got some screenshots from the GUI that aid in attributing different aspects of the model as we work our way through the thermal model setup. So we can use the material database and optical property catalog to prepare each individual component of the geometry for thermal prediction. So yeah, once the model is all set up and ready to run and the weather has been specified, the user is going to specify the start time and end time of the simulation. And it can also be a steady state run where just one temperature or one time step is predicted, and then the boundary conditions at that time are assumed to be infinitely present. But most folks are interested in transient simulation where, you know, they specify a start time, they specify an end time, and a time step size in the middle. So physical temperatures can be solved for, you know, as frequently or infrequently as you want to get the fidelity required for your particular solution. So that's a quick synopsis of MuSES and how target models are set up for thermal prediction. Some of the screenshots shown here are the many different models we've created over the years. And there's a wide variety of different assets that you can contact us about if you'd like further information on, you know, how we can get you a model like this. But as you can see, we've got human dismounts in different positions. We've got tracked and wheeled vehicles. We've got maritime assets, research vessels. We've got drones, fixed wing aircraft, rotary aircraft. So it's a really wide variety of targets, and these are just a few. So yeah, we've got a very big library we've created over time that you can use to maybe get a jump start on analyzing a vehicle in different scenarios if you're interested in that. Okay, so for today's webinar, we're going to focus on one model in particular, which is the Leclerc main battle tank. And this is a French asset designed for armor protected direct fire support. And there's some information shown there with its 120 millimeter autocannon, machine guns, and so forth. The screenshot in the lower left shows the 3D geometry with feature edges turned on. So the mesh isn't actually displayed, but you can get an idea of the level of fidelity and detail contained in the model. And the image in the lower right is the same thing, just colored by part. So you can see the number of components required to represent a model such as this, which gives us the level of control we need to assign boundary conditions for convection and paint codes and heat sources in the appropriate fashion. So these two images are temperature records from a given time step, just to give an idea of where some of the critical component heating happens. So in this case, you can see some heating on the tracks, the road wheels, and the bearings. And this is a rear mounted engine, so you can see some heating in the back coming from the engine and the radiators and the exhaust system. And this should be more apparent in some of the examples we'll show later, but I just wanted to isolate the target and show some MuSES outputs before we hand things off to Pierre, and he discusses how these records get pulled into Oktal for co-simulation. So yeah, the last slide that I just showed depicted a snapshot in time, right? But now we're going to talk about how MuSES can incorporate mission profiles and engine states for transient simulation over a diurnal period. So our software is typically used for transient simulation, and here we're going to be simulating just under an hour. But if you look on the left, that top photo there depicts the engine state of the vehicle. So for this example, the engine is off to start, transitions to idle for 5 minutes, and then it transitions to an exercise state where the vehicle is in motion, stays there for a while, goes back to idle for 5 minutes, and then the vehicle shuts off for the final 10 minutes of the simulation. So it's kind of like a ramp up and a ramp down. And then the curve in the lower left, that's the vehicle speed curve, which would be 0 for all phases of the mission profile except in the exercise state. So the vehicle starts moving at 10 minutes in, and this is accompanied by increased convection coefficients on the outer envelope of the geometry. The speed maxes out at 60 kph, and it looks like it maintains that speed for about 10 minutes. Then it ramps back down to 0 when the engine state transitions back to the idle and off phase. And we can see the culmination of this profile in the animation that's currently playing to show the predictions of MuSES over time, where the engine starts idling, the tracks and bearings start to heat up, once the vehicle starts moving, and so on. So this is the type of information we'll be using in the Oktal example coming up. And on the right-hand side of the slide are just some static images of the exercised vehicle state. And we've set a couple of the parts to be transparent, so you can get a good idea of what's going on inside the vehicle at its peak operating state. So this slide shows the physical temperature prediction at a given time into the mission profile, and the corresponding image on the right is a sensor radiance rendering in the long wave IR band at that same time step of interest, where the grayscale units at the bottom of the image are watts per meter squared steradian. And this kind of shows the full culmination of the MuSES toolchain, where we're taking the physical temperature predictions on the left, and we're combining that with surface property information and MODTRAN atmospheric settings at that given point in time. And we're producing a rendering that depicts what an EOIR sensor in the field would perceive, if it had detected this particular tank. But what if you want to do this, or what if you want to insert this high fidelity target model into a much larger scene with clutter discretes and other high value scene variability? One thing you may want to do is combine this tool with another tool designed for that purpose. So this is the main motivation for coupling MuSES and Oktal-SE Workbench EO. So on the MuSES side, right, MuSES is capable of high resolution 3D geometry for high value targets, where a lot of fidelity is required. It contains a comprehensive heat transfer solution, accounting for all modes of heat transfer. And it can employ active heating components such as engines and exhaust to dynamically affect the hard body and IR signature of the target with first principles physics and numerical methods. On the SE workbench side, right, that's capable of a wide area, expansive cluttered scene, both urban and natural. It's a validated solution for IR sensor rendering. And there are options for real-time GPU-based rendering, or the traditional rendering methods, which we'll cover in a second here. So when we combine these strengths together, we get high fidelity targets with active heating combined with large cluttered scenes, and also a fast method for sharing temperature and radiance information to get accurate outputs. Okay, and with that, I will hand things over to Pierre at Oktal. Take it away, Pierre.
Great. Yeah. Thank you, Scott.
Mm-hmm.
Okay. Yeah. So let's talk about what we do at Oktal. Okay. So first of all, so we like SE at Oktal-SE. We put SE everywhere on our tool, on the name of the company. So our main tool is called the SE Workbench. Which is, so first of all, it's a software. This is what we do at Oktal-SE. We are a software editor, and its purpose is to provide physics-based sensor simulation, so in several domains, electro-optics and radio frequency. So on the electro-optics domain, we cover visible and infrared spectrum, and on the RF, we do radar and GNSS. Okay, so if we have a look at the SE Workbench, so you can see examples of the outputs on the right-hand side of your screen. Image radar and infrared images, small or wider images. So as input, first of all, we take 3D data, so for the whole terrain and for the targets. And then we have a database of materials property. So this is something which is validated. We have physical properties on several domains for a wide range of materials, and then we assign these materials to each elements of the target and of the terrain. So we will get back to that a bit later. Then for to compute the atmospheric condition, we use Motran. So as you can see, in terms of inputs, there is quite a similar workflow as MuSES does. These tools are quite similar. Let's say we're more focused on the wider scene and less on the temperature. So in terms of languages, the tool is based on C++ mostly. We have interfaces to Python. And for the real-time rendering, we also use OpenGL and Vulkan. Vulkan is about to be released. It's not yet ready, but it will be soon. And in terms of outputs, so the first thing we produce is exactly on the EO domain is a matrix of radiance value. So we have each pixels are expressed in the radiance value. So we have the signals in watt per meter square per steradian. So it's first of all, it's a physical mean. And then we have tools to model the sensor pipeline, and that allows us to have an output of the sensor from the input physical mean. So more precisely, that can be an image, for example, visible or infrared or SAR image, or that can be specific values, like on the radar domain, you can get speed, you can get range identification, etc. Okay, so matrix of watt per meter square per steradian value on the EO domain. On the RF, it's an echo of the scene sorted in range gauge with the amplitude and phases values. Okay, we also have the capability to produce massive data sets of sensor images to train AI applications. Okay, so if we go to the next slide. Yeah, okay, so that's this diagram is a view, high-level view of the SE Workbench tools. So behind each bricks here, there is one or several tools. So maybe the main things to understand here before going into too much details is first of all that the solution is comprehensive, meaning that there are modules for every step of the simulation process, from terrain modeling to sensor rendering. Okay, so if we take a closer look, we see that first we have tools to model 3D terrains. Then there are tools to manage targets. So more precisely, it's more importing existing 3D models and, if required, editing the mesh. Then there is a central tool to edit the physical material properties. So that's quite important. So I mentioned the database of materials we have. So this is where, with this tool, where you are going to assign specific materials to each bits of the texture. So that's quite important. And by the way, it's important also to note that this is fully editable. So the users can input their own value if they have values from measurement campaigns, for example. Okay, then we model the atmosphere by using MOTRAN as well. So that's used to compute to solve the transmission and the diffusion of the atmosphere, and then to the radiative transfer. Sorry, I was looking for the word in English. And then from that, we also compute the temperature of the scene. So this is the thermal modeling brick. So there are more precisely two things behind that. So we compute the temperature of the full scene of the terrain. So each we get temperature values for each materials and polygon orientation. So for that, we use the geolocalization on Earth. We use the weather data and time of day and the actual hour. Okay, and by doing that, we compute quite precisely the temperature of the terrain. Then for the targets, we have different ways to do that we will explain a bit later. So all of that will create input data that will be inserted in what we call the 3D synthetic environment. So that's really the core side of the process. From that, we can edit a scenario, and then we can do sensor rendering on several domains. So we can generate laser sensor image. We can generate visible images, infrared, radar data, or GNSS data. Okay, and the tool is quite open, so there are room for APIs at different level. Okay, and there is also the capacity to import MuSES thermal skins. Okay, so next slide. Yeah, so here it's a view of what I've explained. So, but instead of seeing the bricks, the tools, we will see more the process of the workflow. So maybe I'm going a bit quicker on this one. But just to explain roughly, you can see on the screen that we first start to model a 3D terrain from 2D geographic data. So the terrain can be ground or sea, it can be urban scenes or natural scenes. It can be quite wide as well, or quite detailed. Then from that, this is where we do all the aspects of physics. So the atmosphere, the temperature, the physical properties, sometimes some special effects. And this is also where we configure the scenario, sensor positioning, and we import the 3D objects. So from that, we have a ready-to-use synthetic environment. And from the sensor we have positioned, we will proceed to sensor rendering. So you can see on this diagram that there are two ways to do sensor rendering. One is based on ray tracing, and its idea is to be high fidelity. So this is the one with the higher level of physical accuracy. And this second one is quite close in terms of rendering, but the priority is made on the performance, so on the frame rate. And that's based on different technologies, so-called rastering. And the idea is to have the high fidelity mode as a reference. And if you need to do a real-time simulation on your scenario, the high fidelity mode can be compared to the real-time to get the delta, the difference you have in terms of radians for each pixel. And then you can assess if your real-time scenario has a sufficient level of accuracy. Okay, and then this is what we produce before the sensor, and then we have modeled the sensor effect, as you can see, to add some noise or any specific effects of the sensor. Okay, so this is on the IR domain, this example, but that's the same kind of process for any type of sensor. Okay, so next slide. Right, okay, so we have talked about what we do and how we do it. So now let's talk about the outputs. So in terms of output, what you get is basically, as said, the physical signal before the sensor or image after a sensor. So here we can see some examples. We can see that can be, of course, on different spectral domains. So we can see here some colored images. We can see some infrared images, so shortwave, medium wave, or long wave infrared. We can produce some spectral images, so multispectral visible images, for example, radar images, some specific items as water wakes, plumes, clouds, layers, etc. And on the images on the right-hand side, you can see that some are focused on specific targets, but some others are more representing wide scenes, urban zones, industrial area, airports, countryside, desert, sea, etc. So you have quite different types of environments. So that's for the output we produce. But what about the use cases? So why do we produce that? So we address different types of application. So we can mention one which is definitely a growing demand, which is to generate massive data sets for AI applications. Then we also have, as a use case, hardware-in-the-loop application, where the real system is put in the simulation. Secure development, vision-based navigation application on the defense domain, but also on the civilian aviations. Parametric studies is quite done as well, and enhanced vision system for the civilian aviation. So if we go to the next slide. Okay, so that's a few examples of the type of off-the-shelf terrain that we have. So we can model from scratch different backgrounds on demand, but we also have a catalog. So that's examples here of desertic terrain or Middle East type of terrain. Then we have a coastal area, rural area, and an airport. So that's examples of the kind of things we can model. Okay, so next slide. Right, so let's talk about now coupling our tools. Okay, so I mentioned that we have the tools to do the thermal modeling of the terrain, and I briefly mentioned that this is also applicable to targets. So for targets, we either consider that the target is static and not moving on the scenario and for the past 24 hours. So we can consider it as the same way as we do for the terrain. But mostly the targets will be dynamic objects. And in this case, we have a thermal modeling tool, which is descriptive. Okay, so this is done via our tool called SE Physical Editor. Okay, so the main idea is for users to be able to paint, let's say, to paint a thermal skin. Okay, so if you have a look on the top right-hand side image, this car, we can see the temperature texture. So here the user has manually defined the heating zone. Okay, so that's descriptive. So that can be relevant when there is a low requirement for accuracy, or where you have a prior thermal knowledge of the thermal signature of the target before doing the simulation, or when complexity is prohibitive, because this is quite straightforward. But you can face limitation when you do that, when there is a high level of accuracy or where you need a physics-based simulation. Okay, so that's why the coupling can be relevant. Okay, so here we have a summary of the processes of MuSES and Oktal-SE. So it's quite similar in a way. Basically, we both start from 3D models from a real target. Then there is this material attribution. So of course, on the MuSES side, there is more parameters focused on the thermal modeling, whereas in the SE Workbench, you will have more parameters focused on the scenario setup, on the atmosphere, on the temperature of the scene, etc. But it's more or less the same type of process. So then, with that, the output you can see is MuSES output with the different levels of temperatures, and we have the IR images as an output. Okay, and first of all, it's important to note that if we want to couple our two solutions, the first step is to define a common target and a common 3D models we will use. Okay, so next slide. So here we see the integration of the process. Okay, so MuSES would produce a TDF file. Okay, so describing the temperature assigned to the texture and to the 3D geometry. And we will use that on Oktal-SE's SE Workbench as an input data. Okay, so first, if you look on the top of the right-hand side diagram on Oktal-SE side, there is first a 3D model. Okay, and we do the material attribution, but we import the thermal skin from Tytherm. Okay, from MuSES, from thermoanalytics tools. Okay, and we use that as input information in our synthetic environment when we use targets in the environment and when we assign trajectories, for example, to a target. Okay, so next slide. Okay, so this is some examples here. You know, a picture worth 1,000 words, as we say. So here we can see this famous Leclerc tank in one of our 3D terrain. So we have imported here the thermal skin computed with MuSES, and we can see it's highly accurate. And we have imported it in our scenario where we have all the white area and all the details on the urban scene on this example. Okay, so if we go to the next slide, you can see some captures of the images, so of this main battle tank on the road, and we can see the different level of radiance. That's quite interesting. If you look at the roof, for example, the road, the pavement, and on the target itself, we can see that it's quite precise, and that resemble what Scott showed earlier with the thermal modeling. So we can see that the radiance level matches that with the exhaust and the engine, and all these heating parts. Okay, so next slide. Here, this is well, another image, or maybe this is the video. If you press on, okay, sorry, I thought that was the video. The video is here. Okay, so here it's an animation we have created. So
actually, that's a little further down. I think this is just an image.
Okay, yeah, maybe,
yep.
maybe. Okay.
Oh.
Don't worry. Okay.
Spoiler alert, we're going to show you a nice video with this scenescape. So
yeah, I'm excited. That's why I'm talking about the video.
Right.
But yeah, here we can see the full pictures. We can see some cars. We can see the tanks on the bottom of the screen, and we can see the wider area, urban area. Okay, so next slide. Okay, yes. That's the video coming. That's the video coming. Okay, that's I was excited about. Okay, so here it's on the same scene, and we have created a scenario with the tank being animated, and there is a kind of tracking mode of the camera. So the camera is tracking the tank, so we can follow the tank moving on the scene, and we can see the different level of radiances. So that can be interesting for different types of scenario. And if we go to the next slide, we can see, so that's the same scenario, but with another view. Here, the sensor is fixed, is idle. And we can see like this flying view. So that can be suited for different types of application, like UAV detection, recognition, and identification. Well, I mean, when I say UAV, I mean sensors mounted on UAV. that can be also for any types of aircraft embedded sensors, application, etc. So here the sensor is not moving, but as you can see, there are different types of scenario capabilities to make animation on the sensor, on the scene, or whatever you require. So on the next slide. So here is the images we have computed of a drone. So we have this UAV, and we have computed different images at different stages of the heating cycle. So we can see on the same background, we can see low, medium, and high level of temperature, and of course a very different radiance level of the drone. Okay, so next slide. Here is another video of maritime targets. So that's a surface vessel. So on the left-hand side, it's an RGB video of this vessel with the sea, the waves, etc. And on the right-hand side, so it's not that easy to see. I don't know if you can see that on your screen, but you can see the waves around the ship. You can see the wake as well behind the ship. And if you have a closer look on the ship itself, you can see the heating of the exhaust and etc., which is quite accurate. Okay, so next slide. Okay, so hand it over to you, Scott.
Great. Thanks for your concise summary, Pierre. So yeah, now we're going to wrap up by talking about some advanced and future applications and where this integration process can be applied to going forward. If I can advance the slides here. There we go. Okay, so we picked 3 areas to cover briefly. The first is generating synthetic EOIR imagery for AI applications. Then we'll touch on vehicles in motion a bit. And then we'll talk about future possibilities for a joint signature accuracy study. So the first topic, generating synthetic imagery for AI applications. It's generally understood that machine learning algorithms can be trained to automatically recognize a target, but you need a large data set with lots of variation in the imagery in order to train the ATR effectively, like changing the number of pixels on target, the aspect ratio, time of day, season, other sensor parameters, etc. And it's usually difficult to find sufficient measured imagery in the IR with enough variation. So using synthetic imagery is a good way to fill this gap, or even supplement the gaps in measured images taken, on a field test. So if we look at the Oktal scene, on the upper right, and we zoom in on the vehicle of interest, we could take our Leclerc model, or any model of interest for that matter, and insert that into the scene in a number of different positions and really make a robust image set by varying the sensor parameters in the relationship between the sun and the target. Now looping back to earlier in our conversation, we do have a large database of these target assets that exist for MuSES and Oktal users. And these models are pre-attributed with materials, paints, and user scripts that exercise the vehicle depending on the mission profile. And these are ready to go for insertion into any Oktal scene. So the Leclerc is the example model we showed today, but that could easily be swapped out with any other model in our catalog depending on your interests. And then we can use that catalog of models in the numerous Oktal scene descriptions that are already available to you to generate an image chipset in very short order, leveraging the previous work that both companies have done up to this point. So our models span a number of different paradigms, whether that be land, air, or sea. And the same can be said for Oktal's scene development efforts. So the images on the right here, just a couple examples of using both software packages to build up one of these chipsets in a number of different wave bands for training purposes. We've got littoral backgrounds, open sea backgrounds, different operating states, many things changing. And that's just one application of this interesting coupling process. The next application is vehicles in motion. And so both Oktal and MuSES can simulate moving vehicles. So on the right is for MuSES alone. So that's a MuSES background and a MuSES target of a passenger vehicle driving down the road and turning around some trees. And on the left is a standalone simulation from Oktal-SE, showing a moving vehicle that transitions from an off state to an exercise state, using their simple thermally descriptive approach. And when the coupling process is used, it's possible to manage the transition between various thermal states. So the OSE tools allow the user to progressively switch from one thermal state to another. So any exported thermal states from MuSES, either temperature or radiance information, can be imported into the Oktal environment to allow this transition to accurate thermal modeling while taking advantage of Oktal's rich 3D scene definitions. So something we could do in the future is pull these evolving temperature records from the MuSES car, which relies on waste heat power output as the vehicle progresses through the scene, and apply them to the Oktal model on the left. And another one of the future applications that we've discussed is putting some effort towards a signature accuracy study, where we would use one of MuSES's radiometrically correct target models and a physically realistic background from Oktal to do a comparison against measured field test imagery. So this could be useful as a proof of concept for both customer bases. And we would likely, identify and agree on an appropriate field test data set that's maybe readily available to the public, maybe from a NATO study or something of the like. So it can be easily distributed and shared by both US and international defense communities. So to wrap things up here in regards to the MuSES Oktal-SE coupling process, the strengths of MuSES are the high resolution 3D geometry we can handle in an accurate way that takes into account all modes of heat transfer to come up with a very comprehensive physical temperature prediction for high value targets, and the ability to include active heating and mission profiles in our simulation to handle the level of sophistication our customers expect or require. And the strengths of Oktal, as we showed earlier, can handle large, expansive, complex, cluttered scenes. It has an industry verified physical rendering schema that is widely accepted by the EU community, and it can handle intricate sensor platform motion to easily render chipsets or IR video output. So when combined, we can capture the strengths of both tools to incorporate high fidelity targets with active heating into expansive cluttered scenes with the process that we've outlined today. And this gives the analyst a reliable method to pull geometry and temperature information into Oktal for co-simulation purposes and improve the realism and fidelity of their large machine learning data sets, if they're doing anything for training. Yeah, and I'll also mention that we've done this type of a deployment with past customers, and that's usually both teams, working together to deploy this co-simulation process to get their job done. So with that, I'll just wrap up and say thank you to those of you who attended the webinar. And yeah, thanks from the Thermal Analytics crew and from the folks that made this possible on the Oktal side as well. Appreciate it.
Thank you.
All right, thanks, Scott. Thanks,
Yep.
Pierre. First one is the TDF format proprietary?
Oh, yeah, good question. The TDF format is a bit proprietary. It's based on HDF. We do distribute a utility called TDF.io, which allows folks to read info out of those TDF files. So there is a way to get model information out of the TDF file. Yeah.
All right, thank you. What is the time and effort to integrate OSE and MuSES?
Yeah, Pierre, you want to take that one?
Yeah, maybe yes.
Sure.
If you don't mind, then that's a good question too. I would say it's quite short. I mean, I'm taking the lead. It looks like there's a lot on quite an Oktal-SE side on this one. So there is dedicated tool on Oktal-SE for import of 3D format, different formats called SE FFT. And within this tool, there is specific features to integrate TDF files. So it's really like import of external files. So that's quite straightforward. So the effort is quite limited on the import itself. Then of course you have all this modeling effort to model MuSES model and SE Workbench scenes. But then the integration itself is quite straightforward.
Okay, thank you. Let's see here. How do I get a hold of the MuSES target catalog?
Yeah, so that would be available through our sales team. So the easiest way to get that in your hands is by reaching out to your account owner, and they will send you that information promptly. Yeah, it's just a PDF of all the different targets with names and specifications regarding the specific asset.
All right, thank you. Is there any way to manage the scene variability for AI?
Yeah, I can take this one maybe. So if I talk about like Oktal-SE, we have a package called SE Workbench AI. It's a new edition. It's quite new actually. So it's derived from SE Workbench EO or RF. The idea is it's simpler to use, and it's really designed to manage like large data sets, to manage the labels you need when you need to do a data set for AI. And you also manage the variability, the different parameters of your scenario. You manage that as a variable, and then you can set the configuration of your data sets, and you manage the full data sets like that. And so for that, the MuSES targets can be, inserted as input data. Common MuSES and Oktal-SE targets, and that can be used within this scenario. And the different thermal states, whether the engine is off or full on or whatever, you can manage that as a variable as well. So that allows you to have different thermal states as one of the main the several variables you have on your scenario.
All right, thank you. What types of resultant data can be exported from MuSES to use in scene simulation?
Yeah, so MuSES can either export physical temperatures by way of a texture file, or you can export radiance results to the texture file if that's what you're interested in pulling into the scene. And we can choose which time steps we want to export that resultant data for, so the user has some control over which records they want to export. I believe that answers the question.
All right, and what's the relationship between Oktal-SE and thermal analytics?
You want to take that one, Peter?
Yeah. Well, I would say we are quite complementary, aren't we, Scott?
Yeah, I think so.
We've been we've been in the marketplace for quite a long time, and we've always seen each other as a complementary, simulation stakeholders, I would say, and we have quite a long history of collaboration as well with so some interesting success stories, like with several organisms, including several MODs, like the French MOD, for example. So
DGA.
Yeah, the DGA.
All right. Well, that will complete today's webinar. Looks like that's it for questions. So we appreciate you all attending. You all receive a follow-up email containing links to download the presentation slides and watch the recorded webinar session. Looks like I had a couple questions coming here late at the end. I will make sure that we all definitely follow up with you via email afterwards. But again, thank you everyone, and have a nice day.
Yeah, appreciate the
Thank
time.
you. Thank you, everyone.